Good afternoon, I'm Denis Dondi. It's a pleasure for me to be here to present my research on wireless sensor network for industrial application, and in particular energy harvesting system for low power devices. The presentation is organized as follows. I will first introduce the wireless sensor network, and then I will present you the first project on wireless tracking system, and then the main project on energy harvesting system that is split into main blocks, solar energy harvester and an energy harvester for biomedical implants. Then we will talk about conclusion and the list of publications generated. So wireless sensor networks are distributed network of tens, hundreds, or thousands on embedded autonomous devices that communicate one to each other with a wireless radio link. Each embedded device is a quite complex system that collects data from the environment through sensors and elaborates this data with a microprocessor or a microcontroller and transmit this data usually through a wireless link. Wireless sensor network can be applied for very different fields, for example, video surveillance or environment monitoring, industrial application, and automotive monitoring. Due to the complexity of the wireless sensor network system, there are a lot of research that can be exploited on that. For example, the implementation of ultra-low power embedded system, or the implementation of microprocessor or microcontroller, the implementation of real-time operating system on custom protocols, and for example, the implementation of power management system and energy harvesting systems. So the first project for my the research carried out during my PhD refers to the implementation of a wireless tracking system that is a distributed communication system to acquire and deliver information about the localization of mobile vehicles to an area control station. And for example, think about the information about the position of vehicles, just like, for example, a gasoline truck on a landing zone for an airport. So the constraints for this system are the reliability of the information provided to the central station and the delivery delay for the information. So in order to accomplish the constraints, the system has been implemented like the mobile phone networks, and so with a distributed replication of small cells, where in each cells there are a lot of fixed stations that communicate one to each other to collect this data and forward this data to the central station. So due to this implementation, we can define two possible coverage area. An interstation coverage area that refers to the communication between fixed station, and an intrastation coverage area that refers to the communication between mobile devices and the fixed station. In order to implement this kind of system, we need to adopt two different routing protocols. One is the COLSR, that is characterized of a very low propagation delay in order to increase the packet throughput between the fixed station. And the other protocol is the mobile ODV that allow to implement single link and multiple link channel, because two possible scenarios can occur for the communication between mobile vehicles and fixed station. The first one is when the vehicle is inside the coverage area of the fixed station, and so the link can be implemented in a single link, and it's quite simple to communicate. The problem is when the mobile vehicle is outside the coverage area or in a borderline, or for example in this case between several coverage area of neighbors stations. And so in this case the communication link is implemented with a multi-hop channel adopting another mobile vehicle as forwarder. The system has been developed with the NS2 simulator and has been implemented characterizing these protocols, these communication protocols I show you. And in order to validate the design flow, we implemented the system on this embedded hardware platform. It is based on an ARM9 processor and a communication transceiver based on IEEE 802.11 transceiver. With this architecture, we implemented an indoor network of a small size, just only 10 square meter, to validate the system can maintain the network infrastructure. And then an outdoor large-size network with an area higher than 100 square meters to validate that the delivery time is compliant with the specification. Then the main topic of my research that concerns the energy harvesting system. Wireless sensor network has gained a lot of interest during last year, but one of the main problems of this kind of system are their power hungriness. Because since these systems are powered from batteries, recharging batteries or replacing batteries is a very expensive cost, especially for hundreds of thousands of networks. And so several solutions to improve this energy efficiency can be adopted. One is, for example, the development of ultra-low power architectures or the adoption of power-saving algorithms that, for example, reduce the duty cycle or the activity of a microprocessor or wireless interface. But another possible solution is the implementation of an energy harvesting system. Energy harvesting means collecting and storing energy. And since wireless sensor networks are deployed in, for example, outdoor or industrial environments, there are a lot of energy sources, for example, solar or wind in outdoor situation, or piezoelectric, thermal, and radio frequency for industrial application. So we thought that the energy harvesting system can be suitable to extend the battery lifetime, or for example, as I will show you, replace a battery in this kind of system. So concerning the solar energy harvester, this is the main scheme that for the system. We have the photovoltaic panel that convert the energy coming from the sun into electricity, and then a first input stage that collect this energy and store it into an energy buffer. And then an output stage is required to collect, to drain energy from the energy buffer and provide the power supply to the wireless device. The most important things for this kind of system is the energy efficiency, because increasing the energy efficiency allows to increase the power budget for the wireless device, and so to, for example, to reduce the size of the photovoltaic panel to obtain the same level of power at the output. So the first step for this research concerns the implementation, the analysis of the energy sources, that in this case is a photovoltaic panel that can be represented as the connection of several photovoltaic cells in series and parallel. Where, this is the compact model for a photovoltaic cell, and this is the equation that describes the behavior of the cell. Since photovoltaic panel has a non-linear behavior, it's quite complex to predict the amount of power available at the output and how this power changes with the light intensity, for example, and temperature. So I implemented a compact spice model that allow to predict this level of power, of energy, for different light intensity and different photovoltaic panels of phase temperature. These graphs represent the comparison between the measured power at the output of the panel and the estimation from the spice model. And moreover, how you can see from the bottom graph, for each light intensity, so for each curve, there's an optimum working condition that allow to maximize the power collected from the photovoltaic panel. So the SPICE model allows to predict this optimum working condition that is suitable for the design of the system, because we can predict in which kind of working condition the system can work with the maximum efficiency. So the solar energy harvester has been implemented with this architecture. This is mainly based on 3 blocks. The first block is the input stage regulator that collect the energy from the photovoltaic panel and store the energy into the supercapacitor. The second block is the maximum power point tracker, that is a custom analog device system that senses the instantaneous working condition through a pilot cell. That is a small size photovoltaic cell implemented with the same technology of the photovoltaic panel. And through this information and with a custom algorithm, drives the MOSFET switch in order to keep the photovoltaic panel to work in the close neighbor of the optimum condition. Then the last block is the output stage regulator that drains energy from the supercapacitor and also from the photovoltaic panel to provide the power supply for the wireless device connected as load. The implementation of the system has been divided in the analysis of each of the three main blocks. So the input stage architecture is similar to the buck converter. The main difference is that there isn't any feedback from the output to the input. And so during the charging process of the supercapacitor, the ratio between the input voltage and the output voltage changes. And this change implies a change also of the switching period and the switching frequency of the MOSFET, and so the duty cycle. This variation of the characteristic of the system increases the complexity of the analysis, and so I implemented a compact model of the on state and the off state of the circuit, and this model allows to predict the power losses of the system and also to predict the real estimation of the input power for the system. This prediction of these quantities allows to define some design guidelines that helps to optimize the design of the system, because the input stage is the part of the system that collects energy from the photovoltaic panel, so increasing the efficiency of this block allows to increase the overall efficiency. And so following these design guidelines, two optimum input stages has been implemented. The first one is based on ultra-low power architecture. We adopted ultra-low power because we thought that reducing the power consumption of the architecture was helpful to increase the efficiency. But the design guidelines suggested that increasing the switching frequency in certain working conditions is better for the efficiency. And our measurements confirm the efficiency can be increased, increasing the switching frequency. Concerning the second block, the maximum power point tracker, in order to estimate the optimum working condition, there are several algorithms from literature, but most of them are for high power photovoltaic plants, where the estimation of this working condition is not so crucial for the amount of energy required for the estimation. But we decided to adopt this kind of algorithm because it's quite simple and can be implemented with an analog solution. And this is based on an intrinsic characteristic of the photovoltaic devices that says that the maximum power point is located between 70 and 80% of the open circuit voltage. So adopting the pilot cell, we can estimate the open circuit voltage for a certain light intensity and certain temperature. And with this information, we can estimate the maximum power point. And with the circuit implemented, we have an instantaneous information about the working condition of the photovoltaic panel and an instantaneous estimation of the optimum working condition. And so with this hysteresis comparator, we drive the MOSFET switch in order to keep the photovoltaic panel working close to the optimum working condition. One important feature of this part of the system is that all the system is self-powered from the photovoltaic panel, so we don't need any external battery or any external energy source. What is crucial in the design of this block is the trade-off referring to the hysteresis of the comparator, because reducing the hysteresis allows to reduce the voltage window where the photovoltaic panel moves, and so increases the efficiency, the energy collecting efficiency. But with a small window, we are not able to follow very huge variation of the light intensity. For example, if a cloud goes over the photovoltaic panel, the output voltage changes quite quickly, and the system cannot follow this kind of variation. So there's this trade-off between optimum efficiency, optimum level of power collected from the photovoltaic panel, and reliability to the variation of light intensity. The last block is the output stage regulator that is mainly based on off-the-shelf DC-DC switching regulator that allows to generate the output voltage required for the embedded system. The problem with this block comes from the commercial switching regulator are thought to work with stable input voltage. But in our system, the input voltage is the voltage across the supercapacitor that changes during the charging process. And so, implementing several prototypes, we figure out that the variation of the input voltage forces the switching regulator to work in a kind of inefficient condition during the startup, because the energy available at the input is not enough to completely or properly turn on the system. And so we inserted this smart enabling circuit. This is still powered from the photovoltaic panel that senses the amount of energy available in the supercapacitor, and concerning this level of energy, decides to turn on, so to enable the output stage, and so provide the power supply for the output stage. The adoption of the smart enable, as is shown in this graph, allows to increase the efficiency of the harvester of 10 or 15%, because avoid the critical situation during the startup. So to validate all of this design consideration, we implemented several prototypes. This is the last version of the implementation that has been implemented in two different versions, one based on the ultra-low power architecture and one based on the high-speed or high-frequency architecture. Both implementations are adopt the same custom photovoltaic panel that is represented in this picture. We implemented this photovoltaic panel with monocrystalline silicon single cells, rearranging in series in parallel in order to obtain the desired output voltage and output power. And how you can see, in the middle of the panel there is a cell with a different shape. That one is the pilot cell that estimates the instantaneous working condition. And what is common for the whole implementation is so the custom photovoltaic panel, the maximum power point tracker architecture, and also the output stage that generates the power supply. The most important figure of merit for this kind of system is the harvesting efficiency, that is defined as the ratio between the power provided to supplied to the output load and the power stored into the supercapacitor over the power collected from the photovoltaic panel. And another figure of merit is the time required to charge a supercapacitor. That means also the time required to provide the power supply for the load. Characterization of the system has been exploited for different light intensity in order to estimate the real working condition in an outdoor situation. So with light intensity that vary from 400 or 200 to 1,000 watt over square meter. So the two results that I will show you now refers to the application of the photovoltaic of the solar energy harvester to a localization system, and the definition of the harvesting limits for the whole set of light intensity. Concerning the localization system, we adopted the solar energy harvester to provide the power supply for this kind of nodes. This is characterized by a standby power consumption of 1 milliwatt and a full load power consumption of 50 milliwatt. From the information referring to the typical working principle, we calculated that the average power consumption of the system is close to the standby condition. But still, in order to have a reliable characterization of the system, we performed measurement of the full load, the full charge of the supercapacitor while providing 1 milliwatt and 50 milliwatt to the output device. And the efficiency that we can obtain with the high-speed implementation is higher than 90%. What is important to note from these measurements is that the overall efficiency is strongly dependent on the light intensity. This is due to the fact that high-frequency implementation has an higher power consumption, and so reducing the light intensity reduces the power budget at the input, and so the power consumption of the architecture is more affecting the overall performance. On the other hand, the ultra-low power architecture allows a lower efficiency, not only in the maximum value, but also over the whole system function, but is still slightly dependent on light intensity due to the reduced power consumption of the architecture. The other characterization refers to the harvester limits. In this graph, there's a critical working condition for the harvester. So we defined the maximum sustainable load for the harvester, the maximum amount of power you can deliver to the output for a certain light intensity while charging the supercapacitor. So in this graph, there are three main periods. The first one is when the output stage is off, and so all the energy collected from the photovoltaic panel is stored into the supercapacitor, and the efficiency you can reach is very high. Then the output stage turns on, and in this case is providing 100 milliwatts to the load, and so we have an efficiency drops due to the turns on consumption of the DC-DC converter. Then after the properly turns on period has been accomplished for the DC-DC converter, the efficiency continue to increase because the intrinsic efficiency of the DC-DC converter depends on the ratio between the output and the input voltage. So increasing the voltage on the supercapacitor allows to increase the overall efficiency. This is the comparison of the time required to turn on the output stage, and so the time required to provide the power supply for the wireless device at different light intensity. Even if the high-speed architecture has an higher power consumption due to the architecture, we can turn on the output stage and so provide the power supply for the wireless device in a shorter time, as is shown in this graph. The problem is that a break-even point exists between the two architectures. There's this light intensity close to 500 watt over square meter, where the behavior of the two implementation changes one to the other. So for light intensity higher than 500 watt over square meter, the high speed can sustain higher power consumption of the load and can provide higher working efficiency. While reducing the light intensity, we reduce the power budget at the input, and so the power we can deliver to the load is higher for the ultra low power implementation, and also the efficiency is higher for the ultra low power implementation. Then another energy harvester that has been implemented in collaboration with a PFL in Switzerland is an energy harvesting system to provide the power supply for an implantable device that is used to track the brain activity for certain disease. So the power supply is transferred to this implemented device through an inductive link, and my contribution to this system was the implementation of the matching network and the voltage rectifier that allows to convert the 1 megahertz power carrier signal to a DC voltage for the voltage regulator. This is the prototype we implemented at the PFL that integrates on the same PCB where we implemented the custom coil for the implantable device. On the bottom side of the same PCB, we implemented the matching network, the voltage rectifier, and a power limiter or voltage limiter that avoids some overshots of voltage to the electronics. The main feature of this system is that the voltage rectifier is characterized by a working efficiency that's higher of 60% over the whole power range for the load that changes from 1 to 10 milliwatts. These are the system characterization. On the top, there's the measurements of the matching network and the voltage rectifier together for a load power range that varies from 1 to 10 milliwatts. And overall efficiency is quite low because the measurements are close to 20%, and this is due to the efficiency limitation related to the inductive link, because in order to respect the constraints referring to the sides of the coil for being implanted into the brain, we cannot obtain a good correlation between the two coils, and so the power transfer between the external and internal is not characterized with a high efficiency. So, conclusion of my work. The first part was the development of an autonomous tracking system based on the commercial embedded architecture. And then in order to focus on the power management system, I worked on a solar energy harvester, and in particular the one implemented obtained 80 and 90% of efficiency, and demonstrates that the extension of battery lifetime or the replacement of batteries is possible. And this can be a very smart solution for wireless sensor network for their application in daily life. And the last part of my research refers to the implementation of the inductive link for biomedical application. And this is the list of publications generated during the PhD. Thank you for your attention. If you have any question.
Thank you, Dennis. Question? I have a question for you, or a couple of questions. The first question is, could you tell us more about the resolution and advantages of your solution, of tracking solution in outdoor environment compared to GPS, for example? And next question, I can tell you both and then you can reply. The efficiency or the photovoltaic energy, as you know, depends not only on the illumination, but also, especially if you use a series of cells or parallels of cells, depends also on the uniformity of the illumination. Did you consider in your study also these effects or not?
So, for the first question, probably due to the small amount of time, it was not clear. So, in our system, we collect the location information from a GPS module, and then the vehicle as a GPS receiver on board receive the GPS information, and our system collects this information from the vehicle and forward this information to the area control station. So the area control station has a plan of the critical zone and place the location of these moving vehicles depending of the GPS information. Yes. So we are not implementing a localization system. That one was only the collecting architecture. Concerning the photovoltaic question, in our case we adopted single cell implemented in monocrystalline silicon because the fabrication process is more reliable, and so this kind of cell are characterized by similar properties. And also concerning the illumination issue, our custom panel is only, as you can see, 7 centimeter per 7 centimeter. So in our condition, the illumination is quite homogeneous on the surface. Yes, it's not like hundreds of square meter.
Thank you. So let's move with the other presentation. The speaker